Applications of exponential functions. The size of a rat population of a wharf area is growing at a rate of 10% yearly. That's the rate. So it's a growth rate. If there are 200 rats in 2016, that's an initial condition, find how many rats should be expected by 2020. And in what year will there be 2,000 rats? Okay, so you have your exponential function. T equals years after 2016. It's a 10% growth rate. So it's a 1 plus 10%. So that factor is going to be over 1, so it's definitely growth. And then that just simplifies to 1.1. And then so in 2020, that's 4 years after 2016, R of 4 is going to be to put the 4 up there and get out the calculator and multiply this and get this number, which rounds off to 293 rats. Okay, then when will there be 2,000 rats? So we'll solve that by hand later with logarithms, but now we can just use this calculator method. You put the function in y1. You want to know when it's equal to 2,000. Here is the window that I used to get this picture. Here's the exponential function. Here's the year 2000. Where do they intersect? Do a second calc intersect. Second calc intersect. Okay, and then you come up with this. So in about 24 years, a little bit over 24 years, after 2016, there's going to be 2,000 rats. So in the year, you just add 24 to 2016, you get in the year 2040. So that's it. Now we have another example of exponential decay. A substance is decaying at the rate of 15% each day. If there were 50 grams of the substance to begin with, how many grams will remain after 10 days? After how many days will there be half remaining? Or you could say half gone. That is, find the half-life of the substance. So let's let S of t equal grams of the substance present at t days. So S of t equals, the initial amount is 50, and we have the decay rate of 0.15, so we put 1 minus 0.15 in there because the decay rate is 1 minus the decay factor. But that's algebraically the same as saying the decay factor is 1 minus decay rate. You can see that by adding this quantity over here and subtracting this over there, and it would be the same. And so that's 1 minus 0.15, which is 85. Another way to look at it is you can go directly to the 0.85, because if there's each time you have left 85% of what you previously had, that means you're dropping 15% each day. So either way you want to think about it, you get to this number here, the factor. So the amount remaining after 10 days is S of 10, which is 50.85 to the 10th power. And you get out the calculator, and that's approximately 9.8 grams. The half-life That's the time when half remains, or half gone. So here's our function, and there was initially 50 grams, so we want to know when it is that there'll be 25 grams, half of 50. So we'll solve that with logs later, or graphing. So we'll just do it with graphing right now. 50 times 0.85 to the x, and put 25 in y2. Here's a fool around with the window. You know, the y value has to be at least 50 because it starts with 50. So here's your 25 line. Here's the original function, decaying. When does it hit here? The halfway point. You can see that's the halfway point right there, because here's where you start and here's nothing. So halfway in between that's this, and that goes down here. You do a second calc intersect and you get this number, approximately 4.3 days is half will remain. That means the same thing as saying the half-life of the substance is approximately 4.3 days.